All right, we're going to talk a little bit about thermochemistry, which is the chemistry that has to do with energy and temperature. So first thing we want to talk about a little bit is about energy. We've already defined it as the ability to do work or generate heat. And remember that energy is measured in units of joules or calories. And you might have heard of calories before when looking on the back of a food package because those are energy units. Joules is another unit that we use to measure energy as well. And you might have heard about that when in physics class when you learned about kinetic versus potential energy. And those units or those calculations you use joules for an energy unit. The law of conservation of energy states that energy is not created or destroyed, but it just changes from one form to the next. So heat is a type of thermal energy that moves because of temperature differences. Usually it moves from things that are hot to things that are cold until they come into equilibrium, meaning that their temperatures are the same. Specific heat capacity is a term used to define the amount of heat required to raise the temperature of 1 gram of a substance to 1 degree Celsius. It's used to measure heat transfer. And the different substances respond to heat transfer differently. So, in other words, this is a physical property of certain substances. And what we could say is if it heats up or cools off very quickly, it has low specific heat. Or if it heats up or cools off very slowly, it's got high specific heat. So here are some examples of specific heat, again, which is a physical property of substances. Liquid water has a specific heat capacity of 1 calorie per gram degree Celsius. Water as a solid or ice has a specific heat capacity of 0.5 calories per gram degree Celsius. And water as a gas has a specific heat capacity of 0.47 calories per gram degree Celsius. So even water at different states of matter has different specific heat capacities. And here are some other examples: ethyl alcohol, wood, aluminum, glass, and it goes down the list. And this list is ordered from highest to lowest specific heat capacities. So gold has a very low specific heat capacity, meaning it can heat up or cool off very quickly with very little energy needed to heat up 1 gram by 1 degree Celsius. Conversely, liquid water has the highest specific heat, meaning that it takes a long time for it to heat up by 1 degree Celsius. And you've observed that when boiling water. It takes about 10 minutes to boil a pot of water, and the reason why is because it has a high specific heat. Calorimetry is a science when to use to measure the amount of energy. And it uses the law of conservation of energy to calculate the heat energy of a reaction. And again, it abides by the laws of physics, which states that things travel from things that are hot to things that are cold. And the law of conservation of energy means that the total or the amount of energy is constant throughout the entire process. So the heat released by this burner is absorbed by the water. And we assume that the amount of heat released by the burned fuel is absorbed by the water. So there's no heat that's lost. We use this formula to calculate heat. Q, which is heat, equals m times c times delta T. Q, again, is heat, and it's either measured in joules or calories. M is mass, and we measure that in grams. C is the specific heat capacity of that substance, and it's either in joules per gram degree Celsius or calories per gram degree Celsius. And delta T is a temperature difference from the final measurement minus the initial measurement of that substance. Here's an example. So how much energy is required to raise 5 grams of water from 25 degrees Celsius to 75 degrees Celsius? Specific heat in joules per gram degree Celsius is 4.2 grams degrees Celsius, whereas in the table that you saw before that listed all the different specific heats, it had 1 calorie per gram degree Celsius. So it all depends on the unit that you're using. In this case, I want you to calculate the energy in joules. So we're going to use 4.2 joules per gram degree Celsius. So we're looking for Q, which is the amount of energy. We know mass is 5 grams. We know that specific heat, which is given the problem, 4.2 joules per gram degree Celsius. And we know delta T, which is the final minus initial. 75 minus 25 will give us 50 degrees Celsius. So when we calculate that, we go 5 times 4.2 times 50, which gives us 1,050 joules of energy. This is the amount of energy needed, again, to raise 5 grams of water from 25 degrees Celsius to 75, which equals 1,050 joules. You can also calculate it in calories as well. You would just have to substitute 4.2 with 1 calorie per gram degree Celsius, and then I'll give you a different answer. Other vocabulary. Heats of combustion is the amount of heat released by the fuel burned. It's measured in kilojoules per gram. And molar heat of combustion is the amount of heat released by 1 mole of fuel burned, which is measured in kilojoules per mole. Okay, so pay attention to the units. Kilojoules divided by grams, and molar heat of combustion is kilojoules divided by moles. So how to calculate the heat of combustion? In other words, you need to figure out the energy component and then divide that by the mass component of your fuel. So here's your steps. Step 1, you're going to use Q equals MC delta T to calculate the amount of energy released by the fuel, which is absorbed by the water. You're going to convert the kilojoules. You need to convert 2 kilojoules. Remember that 1,000 joules equals 1 kilojoule. So you're going to take your value in step 1 and divide by 1,000. Then you're going to calculate the mass of the fuel burned. You're going to take an initial mass and a final mass of the fuel, and the difference is the amount of fuel that was burned. And then you're going to divide step 2 by step 3, which will give you kilojoules per gram. So here's some example data. If you start off in your calorimeter with a volume of water equal to 100 milliliters, we know that 1 milliliter equals 1 gram, so therefore we have 100 grams of water. We know the specific heat of water is 4.2 joules per gram degree Celsius. If we didn't know that information, we could definitely look it up on any table or textbook. It'll give us that information. We found our initial temperature before we burned our fuel to be 25 degrees Celsius, and after we burned our fuel, the temperature of the water was 78 degrees Celsius. So therefore, the change in temperature, or the delta T, equals 53 degrees Celsius. And we figured out the mass of fuel burned equals 2.78 grams. So how to calculate the heat of combustion? Step 1, we need to figure out the amount of heat released by the fuel into the water. So we're going to use Q equals MC delta T. We know that there's 100 grams of water. We know that the specific heat of water is 4.2, and we know the delta T, or the change in the temperature of the water, was 53 degrees. Therefore, when we calculate that out, we get 22,260 joules. Step 2 is to convert to kilojoules. Well, we have 22,260 joules. We're going to convert that to kilojoules. All we do is take that number, divide by 1,000, and we get 22.26 kilojoules. Step 3 is to calculate the amount of mass of fuel burned, final mass minus initial mass. Well, I didn't tell you the final and initial mass. I just told you the amount of mass of the fuel burned, which is 2.78 grams. So step 4, which is the final step, is to take step 2 and divide it by step 3, and we get 22.26 kilojoules divided by 2.78 grams, and we get 8.01 kilojoules per gram. So for every gram of fuel burned, it gives off 8.01 kilojoules of energy or heat. How to calculate the molar heat of combustion? It's similar to those steps, except there's one more step to add. So again, you're going to use Q equals MC delta T to calculate the amount of energy released by the fuel, which is absorbed by the water. Again, we're trying to figure out the energy component here. We need to convert that into kilojoules. Calculate the amount of mass. This is the same as the calculating the heat of combustion. So you need the final mass and initial mass to subtract those two numbers. This is the step that is different. You need to convert the mass to moles. And the way you do that is you take the mass in grams and divide it by the molar mass of your substance. And that'll give you the number of moles. In step 5, you're going to divide step 2 by step 4. Again, your kilojoules divided by moles. So here's our example data. Again, we've got 100 mils of water, or 100 grams, 4.2 joules per gram degree Celsius. Initial temperature is 25 degrees Celsius. Final temperature is 78 degrees Celsius. We have a change in temperature difference of 53 degrees Celsius, and the mass of fuel burned, which is 2.78 grams. So step 1, we need to find Q. Q equals 22,260 joules. Again, it's the same answer as the previous example. Step 2, we want to convert it to kilojoules, so we're going to take that number, divide by 1,000, we get 22.26 kilojoules. Step 3, we need to calculate the amount of mass of fuel burned, and I just stated what it is. It's 2.78 grams. Here's step 4. You need to convert the mass to moles. So moles equals the mass divided by molar mass. So if our substance or our fuel has a molar mass of 44 grams per mole, then 2.78 grams equals how many moles? So we're going to take 2.78 grams divided by 44 grams per mole, and we get 0.0632 moles. We're on the home stretch here. All we do is divide step 2 by step 4 to get kilojoules per mole. So we get 22.26 kilojoules divided by 0.0632 moles, and we get 352 kilojoules per mole. So in other words, what does this mean? For every mole of fuel burned, you get 352 kilojoules of energy. Again, these two numbers, heat of combustion and molar heat of combustion, mean the exact same thing. You're just changing one unit for the next. Instead of grams, you're using moles for molar heat. Okay, but it's still the amount of energy released in the reaction. Okay, if you have any questions, please ask. And that is the end of this lesson.